Let me ask you something that is going to sit in your brain like a splinter for the rest of the day. Imagine we build a ship, not just any ship, the largest, most ambitious, most expensive object ever constructed by human hands. A vessel kilometers long, carrying 10,000s of our finest, scientists, engineers, doctors, artists, thinkers, dreamers. We pointed toward Proxima Centauri b, the nearest potentially habitable exoplanet just 4.24 light-years away. Sounds close, right? It is not. With our best projected propulsion technology, that journey takes somewhere between 200 and 300 years. That means the people who board that ship will never see the destination. Their children will never see it. Their grandchildren will never see it. We are talking about 12 to 15 generations of human beings living, breeding, aging, and dying inside a metal tube hurtling through the most hostile environment in existence, the interstellar void. Now here is the question that nobody wants to ask. What comes out the other end? What kind of beings step off that ship, if they step off at all, after 3 centuries of isolation, confinement, radiation exposure, genetic drift, social pressure, psychological strain, and total separation from everything that made us human in the first place? The romantic answer is brave explorers, pioneers, the inheritors of humanity's greatest dream. But the scientific answer, the answer supported by genetics, evolutionary biology, psychology, sociology, anthropology, and every isolation study ever conducted, is something far more disturbing. The scientific answer is that generation ships would not create explorers. They would create monsters. And I do not mean that as metaphor. I mean it as biology. Before you think I am being dramatic, before you dismiss this as clickbait pessimism, I want you to consider 3 facts. Fact number 1. NASA conducted the most comprehensive twin study in history using astronauts Scott and Mark Kelly. Scott spent just 340 days on the International Space Station, while Mark stayed on Earth. When Scott returned, researchers found that over 7% of his gene expression had changed. 7%. In less than 1 year. Some of those changes persisted months after his return. His telomeres, the protective caps on his chromosomes, went haywire. His cognitive function measurably declined. His gut microbiome shifted. His immune system behaved differently. That was 1 year, in low Earth orbit, still protected by Earth's magnetosphere. Now multiply that by 300 years in deep space, with no magnetosphere, no protection from galactic cosmic rays, and no return trip. Fact number 2. In 1991, 8 people sealed themselves inside Biosphere 2, an artificial closed ecosystem in Arizona. It was supposed to demonstrate that humans could live in a self-sustaining environment. It collapsed in under 2 years. Oxygen levels dropped dangerously. Carbon dioxide spiked. Crops failed. Insect populations went berserk, with cockroaches and ants overwhelming the system, while pollinators died off. The crew split into hostile factions. They nearly starved. 8 people. 2 years. A closed system on Earth with backup options. Now imagine 10,000 people. 300 years. No backup. No Earth to call for help. Fact number 3. The Mars 500 experiment, conducted by Russia and the European Space Agency, locked 6 men in a simulated spacecraft for 520 days. No real danger. No real isolation. They could leave any time, technically. They knew it was a simulation. And still, crew members developed depression, sleep disorders, cognitive decline. They became sedentary, withdrawn. Social bonds fractured. One crew member experienced a period where he was awake when everyone else slept, and asleep when everyone else was awake, essentially living in his own temporal reality, disconnected from the group. 520 days, in a simulation, with full knowledge that it would end. The people on a generation ship have no such comfort. For them, it never ends. Now, if those 3 facts do not make you deeply uncomfortable about the generation ship concept, you are not paying attention, and we have not even scratched the surface. What I am going to walk you through today is the complete scientific case for why generation ships, far from being humanity's ticket to the stars, might be the most elaborate self-destruction mechanism our species could ever devise. We are going to go through genetics, and I'm going to show you how the human genome unravels in isolation. We are going to go through psychology, and I'm going to show you what happens to minds that are born in cages. We are going to go through sociology, and I am going to show you how every closed society in human history has collapsed or mutated into something unrecognizable. We are going to go through biology and show what deep space does to human flesh over centuries. We are going to go through engineering and show why the ship itself is a ticking time bomb. And we are going to go through ethics and ask whether we have the right to do this at all. By the end, you are going to understand why the beings who arrive at that distant planet would look at an open sky for the first time and feel not wonder, but terror. If this sounds like the kind of deep dive you want to take, if you are the kind of person who wants to understand the real science behind humanity's most ambitious dream and its most disturbing implications, then do me a favor right now. Subscribe, hit the like button, because this is going to be a long journey, and I promise you, it is going to change the way you think about space travel forever. Let us start by understanding what a generation ship actually is, because the concept is both simpler and more terrifying than most people realize. The idea has been floating around in serious scientific and philosophical circles for nearly a century. In 1929, the Irish physicist and crystallographer J.D. Bernal published a visionary essay called The World, the Ship, and the Senses, in which he proposed that humanity's future in space would involve not quick trips but permanent habitation. He imagined hollow spheres miles in diameter, carrying entire civilizations through the cosmos. Around the same time, Robert Goddard, the American rocket pioneer, was privately sketching concepts for what he called an interstellar ark, a sealed vessel designed to carry human passengers across the gulf between stars over multiple lifetimes. The idea was simple in principle. If you cannot make the journey fast enough for one human lifetime, you make the ship big enough to sustain a human population across many lifetimes. The people who launch are not the people who arrive, their distant descendants are. This is not science fiction anymore. Well, it is science fiction in the sense that we cannot build one yet. But it is not science fiction in the sense that serious scientific institutions are actively studying it. DARPA, the Defense Advanced Research Projects Agency of the United States military, funded the 100-year Starship project specifically to explore the feasibility of interstellar travel within the next century. The British Interplanetary Society has conducted two major studies, Project Daedalus in the 1970s and Project Icarus more recently, both designing theoretical interstellar probes and considering the challenges of crewed missions. Academic journals like Acta Astronautica regularly publish peer-reviewed papers modeling generation ship populations, ecosystems, social structures, and engineering requirements. This is real science being done by real scientists, and the more they study it, the more problems they find. Here are the basic numbers. To reach even the nearest star system, Proxima Centauri at 4.24 light-years, with propulsion technology we can reasonably project, fusion drives, nuclear pulse propulsion, solar sails, you are looking at speeds between 1 and 10% of the speed of light. At 1% of light speed, the trip takes over 400 years. At 10%, about 42 years, which is within a single lifetime but requires technology we do not yet possess and may not possess for centuries. For more distant, but potentially more habitable targets like the TRAPPIST, one system at 39 light-years, you are looking at journeys of 400 to 4,000 years depending on speed. The generation ship concept typically assumes journey times of 200 to 1,000 years, meaning 6 to 40 generations of humans. Now here is the first critical number that most people do not think about. How many people do you need? This is not a trivial question. This is in fact one of the most important questions in the entire concept, and the answer is sobering. Cameron Smith, an anthropologist at Portland State University, published detailed research on minimum viable population sizes for interstellar voyages. His conclusion was that you need a minimum of around 10,000 people to maintain sufficient genetic diversity over multiple centuries. Ideally, you want 20,000 to 40,000. Below 10,000, genetic problems become mathematically inevitable within a few generations. Think about what that means for the ship. You need a vessel capable of sustaining 10,000 to 40,000 humans, feeding them, housing them, providing them with air and water, managing their waste, giving them space to live and work and raise children. For centuries, we are talking about a structure that would need to be kilometers in length, carrying millions of tons of equipment, biological material, fuel, and shielding. The International Space Station, the largest structure humanity has ever built in space, weighs about 420 metric tons and supports a crew of 6 to 7. A generation ship would need to be roughly 1,000,000 times larger. Let that number sink in. 1,000,000 times larger than the most ambitious space construction project in human history, and it would need to function flawlessly for 300 years. We cannot even build a car that works reliably for 30. But let us set aside the engineering for now. Let us assume, generously, that we solve the engineering problems. Let us assume we build this magnificent vessel, this cathedral of human ambition, and we fill it with 10,000 brilliant, carefully selected humans, and we launch it into the void. What happens next is where the nightmare begins. And it begins with your DNA. Genetics is merciless. It does not care about your dreams of exploration. It does not care about the mission. It operates according to cold mathematical principles. And those principles are devastating for small, isolated populations. The first thing that happens to our generation ship population is something called genetic drift. In a large population, like the 8 billion people on Earth, random fluctuations in gene frequency are drowned out by sheer numbers. Rare alleles stay rare. Common alleles stay common. The genetic makeup of the population is relatively stable from generation to generation. But in a small population, randomness rules. An allele that is present in 5% of the population might purely by chance end up in 10% in the next generation, or 2%, or 0. This is not natural selection. This is not adaptation. This is pure mathematical noise, and in small populations it is deafening. The founder effect is the first blow. The 10,000 people who board the ship, no matter how carefully selected, carry only a tiny fraction of humanity's total genetic diversity. There are alleles present in the global human population that simply will not be on that ship. They are gone forever. The ship population starts with a reduced genetic palette, and it only gets narrower from there. We have seen this play out on Earth in isolated human populations, and the results are alarming. Consider the Amish of Lancaster County, Pennsylvania. They descend from a small founding population of about 200 Swiss-German immigrants in the 18th century. Today, they have extraordinarily high rates of Ellis-Van Creveld syndrome, a genetic disorder causing short-limbed dwarfism and heart defects. In the general population, this syndrome affects roughly 1 in 60,000 to 1 in 200,000 people. Among the Lancaster Amish, it is roughly 1 in every 200. That is a 1,000-fold increase, caused not by any environmental factor, but purely by the mathematics of small population genetics over roughly 12 generations. 12 generations, the same number of generations our ship crew will go through. Or consider Pingalap, a tiny atoll in Micronesia. In 1775, a typhoon killed most of the island's population, leaving only about 20 survivors. One of those survivors carried a rare gene for achromatopsia, complete color blindness. Today, roughly 10% of Pingalap's population is totally colorblind, compared to a global rate of roughly 1 in 30,000. Again, this is pure genetic drift in a small population, amplified over generations. The gene was not advantageous, it was not selected for, it just happened to be carried by one of the survivors, and random chance amplified it. Now imagine this process running on a generation ship for 300 years. It is not just 1 or 2 conditions that will spike in frequency. It is dozens, hundreds. Every deleterious recessive allele in the founding population has a chance to become prevalent. Conditions that are vanishingly rare on Earth could become common, even universal, on the ship. And new mutations, which we will discuss in a moment, add to the mix every generation. The mathematics of inbreeding depression make this even worse. Even with 10,000 people, the effective breeding population, the number of individuals actually contributing genes to the next generation, is always smaller than the total population. Not everyone reproduces. Not everyone reproduces equally. Some family lines will be more successful than others. Social dynamics, attractiveness, health, role assignments, all of these narrow the effective breeding population. Conservation biologists use something called the 5500 rule, or more precisely the 5500 rule, which states that you need a minimum effective population of 50 to avoid severe inbreeding depression in the short term, and an effective population of 500 to maintain long-term genetic health and evolutionary potential. On a ship of 10,000, the effective breeding population might be 3,000 to 5,000. Over 15 generations, with no influx of new genetic material, heterozygosity, the measure of genetic diversity, will steadily decline. The math is straightforward and unforgiving. In each generation, heterozygosity decreases by approximately 1/2 times the effective population size. With an effective population of 4,000, you lose about 1/8,000th of your heterozygosity per generation. Over 15 generations, that is a cumulative loss of about 0.2%. That sounds small. It is not. That number represents the average across the whole genome. For specific alleles, the loss can be much more dramatic. And the effects compound. Deleterious recessive alleles that are normally masked by dominant healthy copies get exposed as diversity shrinks, birth defects increase, immune system diversity decreases, fitness declines. This is called inbreeding depression, and it has been documented in every small isolated population ever studied, from cheetahs to Florida panthers to island human populations. The generation ship is an island, the most isolated island in the history of life. But here is where it gets truly terrifying. We have been talking about normal genetic processes, drift, founder effects, inbreeding, that happen on Earth in isolated populations. The generation ship adds something that no Earth population has ever faced: cosmic radiation. Outside the protective bubble of Earth's magnetosphere, space is flooded with radiation. Galactic cosmic rays, or GCRs, are high-energy particles, mostly protons and atomic nuclei, that travel at nearly the speed of light. They originate from supernovae, neutron star collisions, and other violent cosmic events. On Earth's surface, the atmosphere and magnetic field shield us from the vast majority of GCRs. On the International Space Station, astronauts receive roughly 10 times the radiation dose of a person on Earth's surface, and they are still partially protected by Earth's magnetosphere. In deep interstellar space, there is no such protection. The radiation environment is roughly 2 to 3 times worse than on the ISS, depending on solar activity and shielding. Here is what GCRs do to DNA. Unlike the X-rays or gamma rays you might get in a medical procedure, GCRs include heavy ions, particles like iron nuclei traveling at relativistic speeds. When a heavy ion passes through a cell, it does not just break one strand of DNA, it shatters both strands in multiple places simultaneously, leaving what scientists call complex clustered DNA damage. This type of damage is extraordinarily difficult for the cell to repair accurately. The cell tries, but the repair is often imperfect, introducing mutations. And these are not minor single nucleotide changes. These are insertions, deletions, translocations, chromosomal rearrangements. The kind of damage that causes cancer, yes, but also the kind that, if it occurs in reproductive cells, gets passed on to the next generation. NASA's Human Research Program has identified space radiation as the single greatest health risk for long-duration spaceflight, outranking even microgravity. Current shielding technology can reduce radiation exposure, but cannot eliminate it. Water, polyethylene, and regolith-based shielding help with some types of radiation, but are largely ineffective against the highest energy GCRs. You would need meters of lead shielding to stop the most energetic particles, and that is simply not feasible for a ship that needs to be lightweight enough to accelerate to a meaningful fraction of light speed. What this means for the generation ship is devastating. Every generation of shipborne humans will experience an elevated mutation rate compared to Earth humans. Every generation. 15 generations of elevated mutation accumulation. Most of these mutations will be neutral or harmful. A very small fraction might be beneficial, but the ratio is terrible. For every one potentially useful mutation, there are hundreds of deleterious ones. And unlike on Earth, where a large population can absorb and dilute harmful mutations, the ship's small population has no such buffer. Harmful mutations can spread through the population via genetic drift even if they reduce fitness. This is called mutational meltdown, and it is a recognized extinction mechanism for small populations. The generation ship, bombarded by cosmic radiation and constrained to a tiny gene pool, is essentially a mutational meltdown machine. And then there are the epigenetic changes, which might be even more insidious because they operate on a faster timescale. Epigenetics refers to changes in gene expression that do not involve alterations to the DNA sequence itself, but rather modifications to how genes are read, chemical tags on DNA and histone proteins that turn genes on or off. The NASA twin study revealed extensive epigenetic changes in Scott Kelly after his year in space. Genes involved in immune function, bone formation, DNA repair, and hypoxia response showed altered expression patterns. Some of these changes reversed after return to Earth. Some did not. And here is the critical point. Epigenetic changes can be inherited. A parent's epigenetic state can influence their child's gene expression. This means that the stress of the ship environment, the altered gravity, the radiation exposure, the artificial light cycles, the recycled air, the psychological pressure, all of this is not just affecting the individual, but potentially programming their descendants. Each generation inherits not just the mutated DNA of their parents, but the epigenetic scars of the ship environment, compounded over centuries. Let me paint you the genetic picture of what arrives at Proxima Centauri b after 300 years. The arriving population has significantly reduced genetic diversity compared to any population on Earth. They carry a unique constellation of genetic diseases, some of which may be entirely novel, conditions that have never existed in any human population because they arose from the specific combination of founder effects, drift, radiation-induced mutations, and inbreeding unique to that ship. Their immune system genes, the MHC or HLA complex, which is one of the most diverse gene families in the human genome and critical for fighting pathogens, have been drastically narrowed. Their bodies have been genetically tuned through both selection and drift to the ship environment. They are, in a very real genetic sense, no longer the same species that launched from Earth. Not in the dramatic science fiction sense of having tentacles or glowing eyes, in the quiet statistical medical sense of having a genome that would produce immune rejection if they tried to receive a blood transfusion from an Earth human. In the sense that their children, if they could interbreed with Earth humans, might show hybrid incompatibilities. In the sense that a geneticist, looking at their DNA, would classify them as a distinct population, possibly a subspecies, of Homo sapiens. And that is if everything goes well. Now forget the DNA for a moment. Let us talk about what happens to the human mind when you lock it in a box and throw away the key for 300 years. The human brain evolved on the African savanna, in an environment of vast horizons, complex social groups, diverse sensory inputs, constant novelty, and real meaningful danger. Every cognitive module in your head, every instinct, every emotional response was sculpted by hundreds of thousands of years of evolution in that environment. The love of exploration, the restlessness you feel when you have been indoors too long, the way a sunset stops you in your tracks, the peace you feel near flowing water, the alertness triggered by rustling in the underbrush. All of it is the savannah whispering in your neurons. A generation ship has none of this. Zero. It has walls, ceilings, recycled air that smells the same every single day, artificial light on a programmed cycle, the same corridors, the same rooms, the same faces, the same food grown in the same hydroponic bays, tasting the same way it tasted yesterday and the day before and the decade before, the same low hum of machinery, forever. No wind, no rain, no seasons, no horizon, no wild animals, no mountains, no oceans, no forests, no thunderstorms, no stars visible to the naked eye except through a window that shows the same unchanging star field year after year, because the stars are so far away that even at 1% of light speed, the constellations barely shift over a human lifetime. Environmental psychology has studied what this kind of sensory monotony does to people, and the results are grim. Humans require a baseline level of sensory novelty to maintain normal cognitive function. Without it, the brain begins to malfunction. Studies in sensory deprivation show that within hours, subjects begin experiencing anxiety, hallucinations, distorted time perception, and difficulty thinking clearly. Now, the generation ship is not a sensory deprivation chamber. There will be sounds, sights, social interactions, but the diversity of sensory input, the richness and unpredictability that characterize the environment we evolved in will be a fraction of what any human has ever experienced in the history of our species. And this is not a temporary condition, it is permanent, lifelong, multi-generational. Research on long-duration confined environments gives us windows into what this does to psychology. Submarine crews on extended patrols of 60 to 90 days show elevated rates of anxiety, depression, irritability, and interpersonal conflict. Antarctic winter overcrews, isolated for 8 to 9 months in research stations, experience what is sometimes called the winter over syndrome, a constellation of symptoms including sleep disruption, cognitive impairment, hostility, depression, and something called the long eye or Antarctic stare, a 1,000-yard stare that indicates profound psychological withdrawal. Crews on the International Space Station, despite rigorous psychological screening and extensive ground support, report loneliness, frustration, and interpersonal tensions during 6-month rotations. And all of these people, every single one, had two things that generation ship inhabitants do not have. They knew it would end, and they had memories of the world outside. Generation 1 of the ship has this advantage. They remember Earth. They remember blue sky and green grass and the feeling of rain on their skin and the sound of birds at dawn. They carry Earth inside them, and it sustains them. It gives their sacrifice meaning. They chose this. They left paradise for the void because they believed in something greater. But their children, their grandchildren, by generation 3, Earth is a story that grandma tells. By generation 5, it is a chapter in a history book. By generation 8, it is a myth. And by generation 12, it might as well be a fairy tale. The people of generation 12 have never experienced anything outside the ship. They have never felt wind. They have never smelled a flower that was not grown under artificial lights in a designated botanical section. The word ocean is an abstraction to them, like the word infinity is to us. You can say it, you can define it, but you cannot feel it. Their entire experiential universe is the interior of the ship. And here is the psychological devastation of that. They have no contrast. They cannot miss what they have never known. But the human brain still craves what it was evolved to need. It is still wired for savannas and forests and horizons. And it is getting corridors and bulkheads and recycled air. The result is a low-grade psychological malaise, not acute enough to look like mental illness perhaps, but chronic enough to color everything. A species-wide depression that nobody can diagnose because everyone has it. A baseline sadness that becomes the new normal. You cannot identify water if you have never been dry. The existential dimension of this is staggering. Let us think about meaning. Viktor Frankl, the psychiatrist who survived the Nazi concentration camps, argued that the primary human drive is not pleasure, as Freud thought, or power, as Adler thought, but meaning. Humans can endure almost anything if they believe it has a purpose. The founding generation of the ship has powerful meaning. They are saving humanity, reaching for the stars, making the ultimate sacrifice for the future. But what about Generation 7? What is their meaning? They were born into a situation they did not choose. They will live their entire lives inside the ship. They will die inside the ship. The destination is something their great-great-great-grandchildren might see. Their entire existence is a link in a chain. They are not explorers. They are not pioneers. They are the fuel burned so that someone else, someday, might get somewhere. How do you find meaning in that? How do you wake up every morning in your metal room, eat your hydroponic breakfast, go to your assigned job maintaining systems you barely understand, interact with the same few hundred people you have known since birth, and believe that your life matters? Some of them will find meaning. Humans are remarkably creative at constructing purpose, but many will not. And across generations, the accumulation of meaninglessness, the weight of purposelessness, will distort the psychology of the population in ways we can barely imagine. Emil Durkheim, the founder of modern sociology, coined the term anomie to describe the breakdown of social norms and values that leads to feelings of purposelessness and alienation. He showed that anomie leads to increased rates of suicide, substance abuse, and social dysfunction. The generation ship is an anomie generator. It takes the very thing that makes human life bearable, the sense that you are going somewhere, that your choices matter, that the future is open, and removes it systematically, generation after generation. And then there is what I call the enclosure effect, which is the psychological inverse of the overview effect. When astronauts see Earth from space for the first time, they experience a profound cognitive shift. They see the planet as a fragile, borderless whole, and it changes their perspective on conflict, politics, identity. Edgar Mitchell, the Apollo 14 astronaut, described it as an explosion of awareness. Ron Garan called it the orbital perspective. It is one of the most consistently reported psychological experiences in spaceflight. Now imagine the opposite. Imagine being born in a box and never seeing anything outside it. Not a planet, not a landscape, not even a parking lot. Your entire visual experience is interior walls, faces, screens, and the unchanging void through a porthole. The enclosure effect would be a profound, lifelong multi-generational cognitive narrowing. The universe shrinks to the size of the ship. Abstract concepts like planet and atmosphere and ecosystem become increasingly meaningless. Words in a database, not experienced realities. The cognitive architecture of the mind reshapes itself around the only reality it has ever known, the inside of a machine. There is research that supports this trajectory. Studies on children raised in institutional settings, Romanian orphanages in the 1980s and 90s, for example, showed that environmental deprivation during critical developmental periods produces lasting cognitive and emotional deficits, reduced IQ, impaired social cognition, difficulty with abstract reasoning, attachment disorders. These children were not genetically different from other children. They were shaped by their environment. And the environment of a generation ship, while hopefully more caring than a Romanian orphanage, shares one critical feature. It is a closed, controlled, monotonous environment with hard limits on exploration, novelty, and sensory richness. Over multiple generations, with each generation raised by parents who were themselves raised in this environment, the psychological profile of the population will drift, not toward madness, necessarily, but towards something deeply, fundamentally different from the psychological profile of any human who has ever lived on Earth. Think of it as domestication. We did it to wolves and made dogs. The ship will do it to pioneers and make something else. The most disturbing psychological prediction is what happens when the ship finally arrives after 12 or 15 generations of life inside a sealed vessel. The humans on board will have developed what amounts to a species-wide agoraphobia. The ship is home. The ship is safe. The ship is everything they have ever known. The planet below, with its open sky and unpredictable weather and alien biology, is the most terrifying thing imaginable. It is literally an alien world to them. They have no instinct for it, no experience with it, no psychological framework for processing it. The first-generation ship human to step outside and look up at an open sky might experience something like a panic attack, an infinite ceiling, no walls, nothing between them and the void of space except a thin atmosphere they cannot see, wind touching their skin, a sensation that has not been felt by anyone they know for 300 years, the smell of alien soil, the sound of alien life. Everything wrong, everything overwhelming, everything screaming danger to a brain that was calibrated for corridors and recycled air. They might refuse to leave. That is the quiet horror buried at the heart of the generation ship concept. After 300 years and 15 generations of sacrifice, the humans who arrive at the new world might look at it, feel primal terror, and turn away. They might choose to stay in the ship. The cage becomes the home. The prison becomes the sanctuary. And the entire point of the mission, to set foot on a new world, fails not because of engineering or genetics or cosmic catastrophe, but because the human mind was reshaped by the journey into something that no longer wants to arrive. Now, if you are thinking about all of this, if you are sitting there recalibrating your assumptions about interstellar travel, I need you to do something for me. Hit the like button, not because I am asking for vanity metrics, but because this conversation matters. The more people who see this, the more people who think critically about the real challenges of space exploration, instead of just watching science fiction and assuming we will figure it out, the better our actual chances of reaching the stars intelligently. And subscribe, because we are only getting started. The social dynamics of the generation ship are, if anything, even more disturbing than the psychology. Let us go there now. Robin Dunbar is a British anthropologist who discovered something fundamental about primate brains. The size of the neocortex, the part of the brain responsible for complex social cognition, directly correlates with the size of the social group the species can maintain. For humans, this number, now called Dunbar's number, is approximately 150. That is the number of stable, meaningful social relationships a human brain can manage. You can know more people than that. You can recognize thousands of faces, but the number of people you can truly know, understand their personality, track your relationship with them, trust and be trusted by, caps out around 150. On a generation ship carrying 10,000 people, Dunbar's number means that the population will inevitably fragment into social groups of roughly 150. These groups will form around proximity, work assignments, family ties, and shared interests. They will develop in-group loyalty and out-group suspicion. They will compete for resources, status, and influence. This is not a design flaw in the social system. This is hardwired human neurology. You cannot train it away. You cannot educate it away. You cannot engineer it away. The ship will tribalize. And tribalization in a closed system with finite resources is a recipe for conflict on a scale that is almost unprecedented in human experience. On Earth, when two groups come into conflict, there are options: migration, trade, diplomacy, avoidance, expansion into new territory. On a generation ship, there is none of that. There is no new territory. There is no option to walk away. There is no distance to create a buffer. Every conflict is a zero-sum game played in a sealed container, where the stakes are not just pride or territory, but air, water, food, and the continued functioning of life support systems. This is not analogous to any conflict scenario in human history. The closest parallels are siege conditions, cities under prolonged military siege, and the social dynamics of those situations are uniformly horrific. Starvation, violence, breakdown of social norms, emergence of warlords and strongmen, hoarding, black markets, betrayal. I want to be clear that I am not saying the generation ship will immediately descend into chaos. Humans are remarkably adaptable, and the early generations, the ones who remember why they are there and what they are doing, will likely maintain social order through shared purpose and institutional memory. But institutional memory fades, purpose erodes, and the mathematical reality of resource constraints in a closed system exerts relentless pressure toward competition. Consider the resource dynamics. The ship has a fixed amount of arable land, or, more likely, hydroponic capacity. It has a fixed water recycling capacity, a fixed oxygen generation capacity, a fixed energy budget. These are hard limits. There is no surplus to speak of, no slack in the system. Every calorie consumed is a calorie that must be produced. Every liter of water used is a liter that must be recycled. In this environment, population control is not optional. It is existential. Someone must decide who reproduces and who does not. Someone must decide how many children each couple can have. Someone must decide what happens if there are too many mouths to feed. These decisions are, by their nature, political. And politics in a closed system with life and death resource constraints becomes politics of the most intense and desperate kind. History shows us what happens. Consider Easter Island, or Rapa Nui, a small isolated population on a tiny island in the Pacific. When they arrived around 800 to 1200 CE, the island was forested and fertile. Over several centuries, the population grew, factions formed, each building increasingly large moai statues as demonstrations of power, and resources were consumed faster than they could regenerate. The forests were cut down, the soil eroded, the birds disappeared, and then the society collapsed into violence. The moai were toppled, a warrior cult emerged. Cannibalism may have occurred. An entire civilization destroyed itself because it was a closed system that could not expand its way out of resource competition. The generation ship is Easter Island in space, with even harder resource limits and even less room to maneuver. The social stratification problem is equally insidious. On the ship, certain jobs are critical. Someone must maintain the engines, someone must operate life support, someone must grow the food, someone must manage the water recycling system, someone must handle waste, someone must govern, and some jobs are more desirable than others. The engineer who understands the fusion reactor is more indispensable than the person who cleans the corridors. The doctor who can perform surgery is more valuable in survival terms than the artist who paints murals on the walls. Over generations, these role distinctions will calcify into social strata. This is not speculation. This is observed in every society that has ever existed. Occupational specialization leads to occupational hierarchy, leads to class structure. On the ship, this process will be accelerated and intensified by the life or death nature of every role. The engineering class will become an elite. They control the systems that keep everyone alive. The agricultural class will become essential but subordinate. The maintenance class will become a lower tier. And beneath them, whatever roles are deemed least essential will become the bottom of the hierarchy. Over 15 generations, these classes will harden. Children will be born into their parents' roles. Mobility between classes will decrease as specialized knowledge becomes jealously guarded. If you are the only family that knows how to repair the fusion containment system, that knowledge is your power, and you do not share it. Intermarriage between classes will become rare. The ship will develop a caste system, not because anyone designed one, but because the pressures of a closed system make it almost inevitable. And caste systems, as we know from every historical example, breed resentment, dehumanization, and eventually rebellion. Power dynamics on the ship will trend toward authoritarianism. This is one of the most robust findings in political science and sociology. Closed systems with no exit option tend toward concentrated power. The logic is simple. In an open society, if the government becomes tyrannical, people can leave. Emigration is the ultimate check on power. The threat of losing your population keeps leaders somewhat accountable. On the generation ship, no one can leave. There is nowhere to go. The airlock is not an exit. It is a death sentence. In this environment, those who control critical resources, energy, air, water, food, have absolute leverage. And absolute leverage, as Lord Acton noted, tends toward absolute corruption. The likely political trajectory is something like this. Generation 1 establishes a democratic or quasi-democratic system with checks and balances, because they come from Earth societies that value such things. Generation 2 maintains it out of respect for the founders. By Generation 3 or 4, resource pressures and tribal factions begin to strain the system. By Generation 5 or 6, a strong leader or faction consolidates power, justifying it as necessary for survival. By Generation 8, the ship is governed by some form of oligarchy or autocracy. Perhaps a council of engineering families who control critical systems. Perhaps a military commander who controls the security forces. Perhaps a religious leader who commands ideological loyalty. By Generation 12, the population has no memory of democracy, no concept of political alternatives, no framework for imagining a different system. The authoritarian structure is simply the way things are, the way they have always been, the way they must be. And the rulers, whoever they are, will use every tool at their disposal: control of information, control of reproduction, control of food distribution, surveillance, propaganda, to maintain their power. Not necessarily out of malice, possibly out of a genuine belief that order must be maintained at all costs, because on a generation ship, disorder really can kill everyone. The knowledge decay problem compounds all of this. Consider what it takes to maintain a generation ship. You need expertise in nuclear physics for the power systems, aerospace engineering for the structure and propulsion, biological sciences for the ecosystem, medical science for the population, computer science for the ship's systems, agricultural science for the food production, chemistry for the water and air recycling, material science for repairs and fabrication. On Earth, this knowledge is maintained by a global civilization of 8 billion people, with thousands of universities, millions of researchers, publishing houses, journals, conferences, cross-pollination of ideas, debate, competition, and constant testing against reality. On the ship, all of this must be maintained by 10,000 people with no external input, no new discoveries from outside, no fresh perspectives, no competitive academic environment, no reality check except the ship's own systems. The history of knowledge transmission in isolated societies is not encouraging. Consider the Polynesian navigators. For centuries, Pacific Island cultures maintained extraordinarily sophisticated navigation knowledge. the ability to cross thousands of miles of open ocean using stars, wave patterns, bird behavior, and cloud formations. This knowledge was transmitted orally from master to apprentice. When isolation increased and the tradition was disrupted, by colonialism, by population decline, by changing social structures, the knowledge was lost within a few generations. By the 20th century, only a handful of traditional navigators remained in all of Polynesia. Thousands of years of accumulated knowledge, nearly erased in less than a century. The generation ship faces the same risk on a far more critical scale. If, in Generation 6, the educational system breaks down because of social upheaval, resource crisis, plague, or simply gradual institutional decay, critical knowledge can be lost within a single generation. And, unlike navigation knowledge, where the consequence of loss is that you cannot find your way across the ocean, the consequence of losing engineering knowledge on a generation ship is that you cannot fix the reactor, or the air scrubbers, or the water recycling system. The consequence is death. Not eventual decline, but relatively rapid death for everyone on board. Even without a dramatic breakdown, there is the more insidious problem of what I would call cargo cult maintenance. The term comes from the cargo cults of Melanesia after World War II, where indigenous peoples who had seen military cargo delivered by airplane began building mock runways and control towers out of bamboo and straw, performing rituals that mimicked the behavior of air traffic controllers. Hoping to summon the cargo back, they replicated the form without understanding the function. On a generation ship, by Generation 10, the engineers maintaining the reactor may be following procedures they learned from their parents who learned from their parents. They know what buttons to push and what readings to look for. They can perform routine maintenance. But do they understand why? Do they understand the physics of fusion containment? Do they understand the metallurgy of the reactor vessel? Do they understand the quantum mechanics of the plasma dynamics? Because if they do not, and something breaks in a new way, not a routine failure but a novel one, they are lost. They are pushing buttons and hoping for cargo, and in the merciless environment of deep space, the cargo does not come. There is a historical parallel that haunts me. In medieval Europe, after the fall of the Western Roman Empire, an enormous body of knowledge was lost. Roman engineering, aqueducts, concrete, road building, architecture, was not maintained because the social and institutional structures that transmitted that knowledge collapsed. For centuries, Europeans lived among Roman ruins they could not replicate. They walked on Roman roads they could not repair. They bathed in Roman aqueducts that slowly crumbled. The knowledge existed in texts, but without the institutions to teach it, practice it, and build on it, it might as well not have existed at all. It took 1,000 years, the Renaissance, to begin recovering what was lost. The generation ship does not have 1,000 years, and it does not have the luxury of living among the ruins. When the ship breaks down, there is no living among the ruins. There is only the void. Cultural evolution on the ship will produce something profoundly alien. Language is the most obvious example. Linguists know that isolated populations show significant linguistic drift within just a few generations. English, as spoken in the United States, diverged noticeably from British English in less than 400 years, and those populations were not isolated. They maintained extensive contact through trade, literature, and migration. An English-speaking population completely isolated for 300 years in an environment radically different from any English has ever been spoken in would develop a dialect so divergent that it would be effectively a new language. Words for Earth phenomena would fade. What use is the word river when no one has seen one in 10 generations? New words would emerge for ship-specific realities, specific sounds the hull makes, specific qualities of the recycled air, specific social dynamics unique to shipboard life. Grammar would shift, pronunciation would drift. By the time the ship arrives at its destination, the people on board would not be able to understand a transmission from Earth without a translator. And then there is religion. I say this not dismissively but as an anthropological observation. Humans are meaning-making creatures, and in the absence of meaning, we create it. The generation ship is an environment stripped of natural meaning. No creation story grounded in landscape, no ancestral homeland, no connection to the cycles of nature that underpin virtually every religion in human history. In this vacuum, new religions will emerge. This is as close to a certainty as any social prediction can be. The question is not whether, but what form they take. The ship's founders may become deified. The original mission documentation may become scripture, reinterpreted, argued over, split into competing interpretations that fuel sectarian conflict. The ship's AI or computer systems, if they are sophisticated enough to interact with the crew, may become objects of worship or fear. The engine room, the life-giving heart of the vessel, may become a temple. The hull, the thin barrier between life and the killing void, may become a sacred boundary. Death rituals, birth rituals, coming-of-age rituals, all of these will develop in ways shaped by the unique environment of the ship. And these religions will not be gentle philosophical frameworks. They will be the kind of intense, all-encompassing belief systems that emerge in high-stress closed environments, demanding, absolutist, intolerant of heresy. Because on a ship where social cohesion is life and dissent can kill everyone, there is enormous pressure toward conformity, and religion is the most powerful conformity engine humans have ever invented. The art of the generation ship would be fascinating but profoundly alien. Every artistic tradition in human history has been shaped by the natural world, landscapes, seasons, animals, weather, the human body in nature, the relationship between humans and the land. Ship art would have none of this. It would be art about walls and corridors, about the hum of machinery, about faces seen too many times, about the void outside the porthole, about the weight of ancestry and the terror of the future. It would be beautiful in its own way. Humans always create beauty, even in the harshest conditions. But it would be beauty we might not recognize. Beauty born of claustrophobia. Beauty born of repetition. Beauty born of a longing for something that has no name, because nobody alive has ever experienced it. Let me pause here to address something important, because I can hear the objection forming in your mind. You are thinking, but we would design for all of this. We would create educational systems, social structures, psychological support, genetic management protocols, recreational spaces, simulated environments. We would plan for these problems. And you are right that we would try. But this objection assumes that a social system designed in the 21st or 22nd century can accurately predict and manage the needs of a human population across 15 generations and 300 years of unprecedented conditions. Consider, can you imagine the social planners of 1726 designing a governance system that would work perfectly in 2026? Could the founding fathers of the United States have designed a constitution that anticipated social media, nuclear weapons, artificial intelligence, and climate change? They were brilliant men working from the best knowledge of their time, and their system has required constant amendment, reinterpretation, civil war, and social upheaval to survive 250 years. And many would argue it is currently under severe strain. The generation ship does not get amendments. It does not get external pressure to reform. It does not get the inflow of immigrants bringing new ideas. It does not get economic growth creating new possibilities. It is a closed system running on initial conditions, and entropy is the only guarantee. Now, let us talk about what space itself does to the human body over 3 centuries, because genetics and psychology are only part of the horror show. The physical transformation of the human species on a generation ship is in some ways the most visceral aspect of this entire discussion. We know what microgravity does to the human body because we have been studying it since the early days of spaceflight. In microgravity, the human body begins to deconstruct itself. Without the constant pull of gravity, bones lose calcium and mineral density at a rate of about 1 to 2% per month. Muscles atrophy, particularly the postural muscles that keep you upright against gravity. The heart, no longer working as hard to pump blood upward against gravity, weakens and shrinks. Fluid shifts toward the head, causing facial puffiness, intracranial pressure increases, and a condition called spaceflight-associated neuroocular syndrome, or SANS, which damages the eyes and impairs vision. The spine elongates as intervertebral discs expand without compression, making astronauts temporarily taller, but also more prone to back injury. The vestibular system, your balance organs, becomes confused without a consistent gravitational reference, leading to spatial disorientation. Now, a generation ship would almost certainly use artificial gravity generated by rotation. The ship, or a section of it, would spin, creating a centrifugal effect that mimics gravity. This is sound physics and well within our engineering capability. But here is the problem. Achieving a full 1G of artificial gravity requires either a very large rotation radius or a high rotation rate. A small ship spinning fast enough to generate 1G would create a strong Coriolis effect. Objects and even people moving within the rotating section would experience strange forces that distort movement and cause nausea. To minimize the Coriolis effect, you need a very large radius, which means a very large ship, which means more mass, more fuel, more construction time, more cost. The practical reality is that different sections of the ship will likely have different gravity levels. The outermost ring might achieve 0.8 G, inner sections might be 0.5 G, or less the central axis would be near 0 G. This means the ship's population will live in a variable gravity environment, with most areas providing less than Earth gravity. And here is what happens to the human body over multiple generations in reduced gravity. The body adapts. This is what bodies do. If you do not need as much bone density because gravity is only 0.7 G, then over time, developmental plasticity and eventually genetic selection will produce humans with less bone density. If your heart does not need to be as strong because it is pumping against less gravity, the heart adapts. Smaller, weaker, more efficient for the reduced load. Muscles adapt. The entire musculoskeletal system recalibrates to the gravity it actually experiences. In a single generation, these changes are plastic. The body responds to the environment, but the underlying genetics are unchanged. Give that person 1G again, and their body can readapt with difficulty. But over multiple generations, the changes become genetic. If thinner bones are not disadvantageous in 0.7 G, and they are not because the body does not need them, then there is no selection pressure to maintain thick bones. Individuals with naturally thinner bones save metabolic energy. They need less calcium. They are slightly more efficient in the ship environment. Over 15 generations, the population's skeletal system will trend toward what is optimal for 0.7 G, not 1G. The same process applies to muscle mass, cardiovascular capacity, respiratory capacity, and every other system that is calibrated to gravitational load. The result is that the humans who arrive at the destination planet will have bodies adapted to the ship's gravity, not the planet's gravity. If the destination planet has Earth-like gravity of roughly 1G, the arriving population will be physiologically devastated. Their bones will fracture under the increased load. Their hearts will strain. Their muscles will be inadequate. Their blood pressure regulation will be wrong. They will be, in physical terms, disabled. Unable to function on the planet they traveled 300 years to reach. The supreme irony, they are adapted to their prison and cannot survive in freedom. And this is assuming the ship's gravity is consistent and well managed. If there are periods of gravity disruption, mechanical failure of the rotation system, power outages, structural damage, the crew will experience variable gravity and potentially extended periods of microgravity. Every such period accelerates the physical degradation, and the effects compound across generations. A generation that experiences a year of reduced gravity due to a mechanical failure will develop in subtly different ways, and those developmental differences will shape their children's development, and so on. The radiation issue deserves deeper examination from a bodily perspective. We discussed the genetic implications, but the immediate physical effects are equally devastating. Galactic cosmic rays do not just damage DNA, they damage tissues, they increase cancer rates, they damage the central nervous system. NASA-funded research has shown that exposure to GCR-level radiation causes cognitive decline in animal models, reduced learning ability, impaired memory, increased anxiety. A 2019 study published in eLife found that mice exposed to chronic low-dose radiation similar to deep space conditions showed progressive cognitive impairment over 6 months, along with measurable changes in brain structure. Extrapolate this to a human population exposed to elevated radiation for an entire lifetime, for 15 lifetimes in succession, and you have a population experiencing chronic, low-grade neurological degradation. Not enough to prevent functioning, perhaps, but enough to reduce cognitive sharpness generation over generation. Enough to make abstract reasoning a little harder, complex problem-solving a little slower, innovation a little less likely. In a population that desperately needs to maintain its technical knowledge across centuries, this is catastrophic. Cancer will be a constant companion. On Earth, cancer is already a leading cause of death. In the high radiation environment of deep space, Cancer rates will be significantly elevated. This changes the entire demographic structure of the ship. If cancer reduces average life expectancy from, say, 75 to 55, the social implications are enormous. People will need to have children younger. They will need to train their replacements earlier. There will be fewer elderly mentors to transmit accumulated wisdom. The population will be younger, on average, with less experience and less accumulated knowledge at the top. Combined with the knowledge decay problem, this creates a society that is increasingly youthful and increasingly ignorant, a dangerous combination for a civilization that depends on maintaining complex technical systems. The immune system deserves its own consideration. On Earth, the human immune system is trained by exposure to an enormous diversity of pathogens, bacteria, viruses, fungi, parasites. From the moment of birth, the immune system is in a constant state of education, learning to distinguish friend from foe, calibrating its responses, building a vast library of immunological memory. This education requires exposure. Without it, the immune system is like a soldier who has never trained, present but incompetent. On a generation ship, the microbial environment will be radically impoverished compared to Earth. The ship will be as sterile as possible. It has to be, because a major epidemic in a closed system with limited medical resources could be an extinction event. But this sterility is a double-edged sword. With each generation, the population's immune systems will have less to train against. Epigenetic changes will reduce immune gene expression. Genetic drift may reduce diversity in the MHC complex. Over multiple generations, the immune system of the ship population will atrophy, not from disease, but from the absence of disease. This creates a horrifying scenario upon arrival. The destination planet, whether it has native life or not, will have a microbial environment completely foreign to the ship population's immune systems. Even if the planet has been seeded with Earth microorganisms through terraforming, 300 years of independent microbial evolution will have produced strains that the ship population has no defense against. The arriving population would face the same immunological catastrophe that devastated indigenous peoples when Europeans arrived in the Americas, except possibly worse, because the immune atrophy would be even more severe. H.G. Wells wrote The War of the Worlds, with the Martians dying from Earth bacteria. In the generation ship scenario, we are the Martians. Let me also discuss the reproductive dimension, because this is where the biological, social, and ethical threads converge in the most uncomfortable way possible. Reproduction on a generation ship cannot be natural. By natural, I mean left to individual choice and chance. The resource constraints of the ship require population control. Too many people means not enough food, water, air. Too few people means not enough genetic diversity, not enough labor, not enough specialists to maintain critical systems. The population must be maintained within a tight band, not too many, not too few, for 300 years. This means that reproduction must be managed. Someone, some system, must decide who has children, when, and how many. This is eugenics. There is no way around it. The word carries the stench of the 20th century's worst atrocities, and rightly so. But on a generation ship, it is not ideological. It is mathematical. If genetic diversity falls below a critical threshold, the population dies. If the population exceeds carrying capacity, people starve. The ship must practice eugenic management not because of some ideology of racial purity, but because the physics of a closed system demands it. What does this look like in practice? Perhaps a genetic database that matches potential parents for maximum diversity. Perhaps a lottery system for reproduction rights. Perhaps mandatory genetic screening with selective embryo implantation. Perhaps, as generations pass and the technology for artificial reproduction improves, a move away from natural conception entirely. Children grown in artificial wombs from optimized genetic combinations, raised by the community rather than by biological parents. Each of these approaches has profound social and psychological consequences. What happens to love when you cannot choose to have a child with the person you love? What happens to family when children are assigned, not born? What happens to identity when your genetic composition was designed by a committee? The reproductive regime of the generation ship, whatever form it takes, will fundamentally reshape the social structure of the population. Family, romance, parenthood, childhood, the most intimate and foundational aspects of human experience, will all be subordinated to the survival calculus of the ship. And the psychological effects of this, compounded over generations, are almost impossible to predict, but they will be profound. The humans who emerge from this system will have a relationship to reproduction, family, and intimacy that bears no resemblance to anything in human history. Now let us zoom out and look at the ship itself as an engineered system, because the ship is not just a setting for this story. The ship is a character, and it is a character that is slowly dying. The first thing to understand is that no machine humans have ever built was designed to operate continuously for 300 years. The oldest continuously operating machines in the world are things like water wheels and clockwork mechanisms, relatively simple devices made of durable materials. The most complex machines we have ever built, spacecraft, nuclear power plants, computer systems, have operational lifespans measured in decades, not centuries. The International Space Station, our most ambitious space construction, was designed for a 15-year lifespan. It has been extended to over 25 years and is showing its age. Air leaks, degraded solar panels, aging hardware. It has been continuously maintained, repaired, and resupplied by Earth throughout its life. A generation ship gets none of that. Every system on the ship is subject to the second law of thermodynamics. Entropy increases, order degrades, seals degrade, metals fatigue, electronics fail, lubricants break down, filters clog, bearings wear. Over 300 years, every component on the ship will fail. Many will fail multiple times. The ship must be able to manufacture replacement parts on board, which means it needs fabrication facilities, raw materials, and the knowledge to use them. If any link in this chain breaks, if the fabrication facility fails, if a critical raw material runs out, if the knowledge to manufacture a specific part is lost, the cascading consequences could be fatal. The ecological systems of the ship are perhaps the most fragile component. The ship must maintain a closed-loop biosphere, air recycling, water recycling, food production, waste processing, for 300 years. Biosphere 2, the most ambitious closed ecosystem experiment in history, failed comprehensively. Oxygen levels dropped from 21% to 14%, equivalent to living at an altitude of 5,300 meters. Carbon dioxide reached levels that impaired cognitive function. Morning glory vines and other aggressive species took over, choking out food crops. Most pollinating insects died. Cockroach and ant populations exploded. Soil microbe composition shifted in destructive ways. And this was a 3.14-acre facility on Earth's surface with abundant sunlight and the option to import emergency supplies, which the crew eventually did. A generation ship's biosphere will be larger but face the same fundamental challenges. Closed ecosystems are inherently unstable. They lack the buffering capacity of a planetary ecosystem, where the sheer scale and diversity of life smooth out fluctuations. In a small closed system, a single disease hitting a staple crop can cause famine. A miscalibration in the atmospheric processing can cause oxygen depletion or CO2 buildup. An invasive microbe can devastate the food chain. A failure in the waste processing system can contaminate the water supply. Each of these events is not a matter of if, but when, over a 300-year timeframe. The ship will also face external threats. Interstellar space is not empty. It contains dust, gas, and occasional larger debris, micrometeoroids, small rocks. At the ship's velocity, even a particle of dust carries enormous kinetic energy. A grain of sand hitting the hull at 1% of light speed impacts with the energy of a small bomb. The ship will need shielding. A thick bumper layer, electromagnetic deflection systems, perhaps a forward shield of ice or rock. But over 300 years that shielding will erode. Millions of tiny impacts will degrade it, and a single larger object that slips through could puncture the hull, decompress a section, and kill hundreds in seconds. The probabilistic analysis of catastrophic events over a 300-year journey is grim. Any single event, hull breach, reactor failure, biosphere collapse, epidemic, civil war fire, might have a relatively low probability in any given year, say 1% per year for a catastrophic event. Over 300 years, the probability that at least one catastrophic event occurs is 1 minus 0.99 to the 300th power, which is approximately 95%. 95% probability of at least one potentially mission-ending catastrophe. And each catastrophe, even if survived, degrades the ship's systems and the population's capacity to handle the next one. Now, I want you to sit with something for a moment, because we have been building this picture piece by piece: genetics, psychology, sociology, biology, engineering, and I want to bring it all together into a single, coherent image of what arrives at the destination after 300 years. Imagine you are standing on the surface of Proxima Centauri b. You have come by some faster means. Perhaps you were sent later on a faster ship, or perhaps you are a purely hypothetical observer. You watch the generation ship enter orbit. After 300 years of travel, it is battered. The hull is pitted by millions of micro-impacts. Sections have been sealed off after decompression events. The exterior shows patches, repairs, jury-rigged modifications accumulated over centuries. It is a ship of Theseus. Virtually every component has been replaced at least once, and the replacements are not as good as the originals because the manufacturing capacity has degraded. A shuttle descends from the ship. The door opens, and what steps out is human, recognizably, undeniably human. 2 arms, 2 legs, a face with 2 eyes and a mouth. But different. They are taller. Generations of lower gravity have elongated their frames. Their limbs are thinner, their muscles less defined. Their skin is pale, almost translucent. 300 years without sunlight, without UV exposure, with no evolutionary pressure to maintain melanin production. Their eyes are large, adapted to the dimmer lighting conditions of the ship's interior. They move with a strange, tentative gait. The gravity of the planet is unfamiliar, heavier than anything they have experienced. Some stumble, some fall. One curls into a fetal position, overwhelmed by the open sky above. They speak, but you cannot understand them. Their language shares some roots with English, but has diverged beyond mutual comprehension. Their social dynamics are immediately apparent and alien: rigid deference to certain individuals, coded gestures you do not recognize, a collective orientation that seems to subsume individual identity. They flinch at the wind. They recoil from the sunlight. One touches soil for the first time and begins to weep, though whether from wonder or terror, you cannot tell. Medical scans reveal a population riddled with genetic conditions unknown on Earth. Their immune systems are naive, childlike. Their bone density is insufficient for sustained activity in 1G. Their cardiovascular systems are struggling with the gravitational load. Within weeks, the first infections begin. Common soil bacteria that an Earth human's immune system would swat aside without noticing are causing sepsis in the shipborne population. Within months, the first cancer clusters appear, exacerbated by the planet's UV radiation, which their bodies have no defense against. Psychologically, they are institutionalized. The open spaces terrify them. The randomness of weather, wind, rain, temperature fluctuation, triggers anxiety responses. They cluster together, seeking the walls and ceilings of their shuttles and prefabricated habitats. Some refuse to leave the structures at all. Others venture out but return quickly, overwhelmed. Their decision-making patterns are collective, rigid, hierarchical. They do not adapt well to novel situations because their entire culture is built around routine and procedure in a controlled environment. Innovation is not valued in their society. Obedience is. Novelty is not exciting. It is threatening. Their social structure is a rigid caste system organized around ship functions that no longer exist. The engineer caste is the ruling class, though many of them no longer understand the engineering they nominally oversee. The agricultural caste tends the food production, clinging to hydroponic methods even as the alien soil beneath their feet might support agriculture, because they have no experience with soil-based farming and no cultural framework for trying something new. The maintenance caste performs the labor, and they are the lowest status, barely regarded as full members of the community. There are religious leaders who interpret the mission texts, garbled, mythologized versions of the original mission documentation, and their interpretations carry the force of law. These are not monsters in the Hollywood sense. They do not have fangs or claws. They are not villains. They are the product of 300 years of physics, biology, and human nature operating in a closed system. They are what happens when you take a species evolved for open savannas and coral reefs and mountain ranges and force it to live in a submarine for 12 generations. They are adapted, they are survivors, but they are not us, and we are not them. And the planet beneath their feet, the paradise we sent them to find, is as alien and hostile to them as the surface of Mars is to us. That is the generation ship. That is what arrives, not explorers, not pioneers. Something else. Now I want to pivot to something that might seem contradictory after everything I have just described. I want to push back against my own argument, because science demands that we consider the strongest objections, and there are objections worth considering. Am I being too pessimistic? Is it possible that I am underestimating human ingenuity, resilience, and adaptability? Let us examine the strongest counterarguments honestly, because this is not about proving a thesis at all costs. This is about understanding reality. Counterargument 1. We would engineer solutions. Gene banks, frozen embryos, genetic screening, CRISPR-based gene editing could theoretically maintain genetic diversity and prevent mutational meltdown. If the ship carries a frozen repository of human embryos or gametes from a diverse global population, the effective genetic population could be orders of magnitude larger than the actual living population. This is a real and powerful objection. The technology for long-term cryopreservation of genetic material exists and is improving. If the ship can maintain a gene bank and periodically introduce stored genetic diversity into the living population, many of the worst genetic scenarios could be avoided. But cryopreservation for 300 years has never been demonstrated. Equipment fails. Power outages can thaw samples. Radiation damages frozen DNA just as it damages living DNA. The gene bank itself is a single point of failure. One catastrophic event, one prolonged power loss, and it is gone. And even if the gene bank survives, using it requires sustained technical capability in reproductive medicine for 300 years. If knowledge decay erodes the ability to perform in vitro fertilization or embryo implantation, the gene bank becomes useless frozen tissue. Counter-argument 2. Artificial intelligence and automation could compensate for human limitations. A sufficiently advanced AI could maintain the ship's systems, manage the biosphere, preserve and transmit knowledge, provide psychological support, and even govern the ship. This would remove many of the human failure modes, knowledge decay, political corruption, social collapse, from the equation. But an AI that is powerful enough to run a generation ship is powerful enough to become the de facto ruler of the ship. The social dynamics of 10,000 humans living under the governance of a machine intelligence are completely unprecedented and deeply unpredictable. What happens when the AI's decisions conflict with human desires? What happens when a faction decides to shut down or reprogram the AI? What happens if the AI develops goals that diverge from the mission? And who maintains the AI? Hardware degrades. Software accumulates bugs. Even if the AI is initially flawless, 300 years of operation without external updates or debugging will produce drift. The AI itself becomes a liability over time. Counterargument 3. We are underestimating human social resilience. Humans have maintained complex societies in harsh conditions for millennia. Indigenous peoples in the Arctic, in deserts, on tiny islands, have built stable cultures that lasted for thousands of years. If they can do it, why not a ship population? This is the strongest counterargument, and it deserves serious respect. Humans are extraordinarily adaptable. We have thrived in environments from the Sahara to the Arctic to the deep jungle. Our social flexibility is unmatched in the animal kingdom, but every one of those successful adaptations had something the generation ship does not: an open system. Arctic peoples could hunt new animals, find new fishing grounds, trade with distant communities, migrate when conditions changed. Even the most isolated island populations had the ocean, the sky, the weather, the seasons. They had an environment to interact with, to draw meaning from, to adapt to. The generation ship is the first truly closed human environment in history. No outside input, no environmental variation, no new resources, no escape. This is not something humans have ever been tested against at the multi-generational scale. The counter-argument assumes that past adaptability predicts future adaptability in an environment that has no precedent. That is a risky assumption. Counter-argument 4. The psychological and social problems are solvable with proper design. Virtual reality environments could simulate open spaces and natural environments. Rotational duty assignments could prevent caste formation. Democratic safeguards could prevent tyranny. Educational systems could preserve knowledge. Each of these is plausible in Generation 1. Each becomes harder to maintain in each successive generation. Virtual reality is an engineering system that requires maintenance, power, and expertise. Rotational duty assignments conflict with the specialization that efficiency demands. Democratic safeguards require a population that values democracy, and there is no guarantee that a population raised in a survival-focused, resource-constrained environment will prioritize individual freedom over collective security. Educational systems require teachers who understand what they are teaching, and the understanding erodes as the living connection to original knowledge grows thinner. The honest summary is this: every problem I have described has a theoretical solution, but every solution is itself a complex system that can fail, and the generation ship requires all of these solutions to work simultaneously for all of 300 years. It is a system of systems, and the failure of any one component can cascade into the failure of the whole. The optimistic case for the generation ship requires everything to go right. The pessimistic case requires only one thing to go wrong. In a 300-year mission, the pessimistic case is not just plausible, it is probable. So where does this leave us? If generation ships produce monsters, not explorers, then how do we reach the stars? This is not a counsel of despair. This is a call for clearer thinking, because the alternatives to generation ships are not just science fiction dreams, they are active areas of serious scientific research, and some of them are far more promising. The first alternative is the embryo ship, sometimes called a seed ship. Instead of sending living humans, you send frozen embryos, tens of thousands of them, representing the full genetic diversity of humanity, stored in cryogenic facilities, maintained by automated systems. Upon arrival at the destination, the embryos are gestated in artificial wombs, a technology that is currently in early development but making rapid progress. And the first generation of colonists is raised by AI systems designed for the purpose. This approach eliminates every generation ship problem. No genetic drift, because the embryos carry full diversity. No psychological institutionalization, because the first conscious humans experience the planet, not the ship. No social collapse, because there is no society on the ship, just cargo. No knowledge decay, because the knowledge is stored digitally and transmitted to the first generation upon arrival. The technical challenges are significant: artificial wombs, AI child-rearing, long-duration cryopreservation, but they are engineering problems, not fundamental conflicts with human biology and psychology. The ethical challenges are also significant, and I do not want to gloss over them. Growing children in machines and raising them with AI instead of human parents raises profound questions about the nature of childhood, attachment, and psychological development. Would these children be psychologically healthy? Would they form normal social bonds? Would they feel a sense of belonging and purpose? These are not trivial questions, but they are questions about the first generation only. Every subsequent generation would be raised by humans, on a planet, in an environment at least somewhat analogous to Earth. The damage, if there is damage, is limited and potentially recoverable. The generation ship's damage accumulates for 15 generations with no recovery. The second alternative is the sleeper ship, cryonics, suspended animation, put the crew to sleep, and wake them up when they arrive. This eliminates the generational problem entirely. The same people who launch are the people who arrive. No genetic drift, no social collapse, no psychological institutionalization, no knowledge decay. The technical challenge is obvious. We cannot currently freeze and revive a human being, but cryopreservation research is advancing. Vitrification, the process of cooling biological tissue so rapidly that ice crystals do not form, has been demonstrated in organs and small organisms. The problem is not physics. There is no physical law that prevents suspended animation. It is engineering and biology. And unlike the generation ship's problems, which are inherent and compounding, the cryonic challenge is binary. Either we solve it, or we do not. If we solve it, the sleeper ship works. Period. The third alternative is digital consciousness transfer. upload human minds to a computer system, transmit them at the speed of light, or near it to a receiver at the destination, and download them into biological or synthetic bodies upon arrival. This eliminates not just the generational problem, but the travel time problem. Transmission at light speed reaches Proxima Centauri in 4.24 years, not 300. The challenges are immense. We do not know if consciousness can be digitized. We do not know if a digital copy is the same person. We face profound philosophical questions about identity and continuity. But if it is possible, it is the cleanest solution by orders of magnitude. The fourth alternative is simply faster propulsion. If we can accelerate a ship to 10% of light speed, Proxima Centauri is a 42-year journey, a single long human lifetime, difficult, stressful, requiring significant life support engineering, but within the range of one generation. No multigenerational problems at all. Breakthrough Starshot, a project funded by Yuri Milner, is already developing laser-propelled light sails that could reach 20% of light speed. Granted, these are tiny probes, not crude ships, but the physics of laser propulsion scales. Nuclear pulse propulsion, as designed in Project Orion, could theoretically achieve 3 to 5% of light speed for a large vessel. Fusion drives, antimatter drives, and technologies we have not yet invented could push this higher. Investing in propulsion technology may be far more productive than investing in generation ship design. The fifth alternative, and the most philosophically challenging, is to stay home, not forever. But for now, the generation ship concept is, in some ways, a fantasy of escape, the idea that we can flee the problems of Earth by running to the stars. But the stars are not going anywhere. They will be there in 1,000 years, in 10,000 years. If we spend the next few centuries making Earth sustainable, advancing our technology, and growing as a civilization, we will be vastly better equipped to reach the stars when we finally go. The weight calculation, developed by Andrew Kennedy in 2006, formalizes this intuition. He showed that for any given destination there exists an optimal departure time that minimizes total travel time, accounting for the possibility that future faster ships could overtake earlier slower ones. Launching too early means being overtaken. Launching too late means unnecessary delay. The optimal point depends on the rate of technological progress. But for plausible assumptions, the optimal departure for a mission to Proxima Centauri might be decades or centuries in the future. Patience in this case is not cowardice, it is strategy. There is a sixth possibility that I find both the most unsettling and the most honest. Perhaps we are not meant to go, not meant in any teleological or mystical sense. I mean that the constraints of biology, psychology, and physics may simply be incompatible with interstellar colonization by biological humans. Perhaps the stars are reachable only by our machines, our probes, our AIs, our robotic emissaries. Perhaps the role of biological humanity is to be the cradle, and the role of our technological children is to be the explorers. This is not a comforting thought. We want to go ourselves. We want to stand on alien soil and breathe alien air and see alien sunsets. But wanting something does not make it physically possible, and the generation ship concept, when examined honestly, may be a monument to our desire to go, rather than a viable plan for going. Let me bring this to a close with a thought that has been burning beneath this entire discussion. The generation ship is not really a problem of engineering. It is not even really a problem of biology or psychology. It is a problem of identity. When we talk about humanity reaching the stars, what do we mean by humanity? Do we mean our DNA, our culture, our values, our consciousness, our physical form? Because the generation ship preserves some of these and destroys others. The DNA will be altered but present. The culture will be unrecognizable. The values will have shifted beyond prediction. The consciousness will be human but shaped by experiences no human has ever had. The physical form will be changed if the beings who arrive at Proxima Centauri be are genetically distinct, culturally alien, psychologically institutionalized, physically adapted to a different environment, and separated from Earth by 300 years of divergent evolution. In what sense have we reached the stars? We sent a seed. Something grew, but it is not us. It is something new, something adapted to the dark. Something that might rightly call the ship home and the planet exile. Something that might look back toward a star called Sol and feel nothing, because Earth is a word in an old book and the sun is just another point of light in a sky that terrifies them. Are they monsters? That is the word in the title, and I have spent all this time building the case for it. But now at the end, I want to complicate it. No, they are not monsters. Monsters are moral judgments, and these beings have done nothing wrong. They are survivors of the most extreme selection pressure any human population has ever endured. They are the product of our ambition and our arrogance. They are what happens when an irresistible force, human curiosity, meets an immovable object, the laws of physics. They are, in the most literal sense, our children, and like all children, they did not ask to be born. They did not ask for the world they inherited. They simply live in it, making the best of what they were given. The monstrosity, if there is one, is not in them. It is in the decision to send them. It is in the hubris of a generation that looked at the stars and said, "We will go," even if it destroys what we are. It is in the willingness to sacrifice 12 generations of human beings, to condemn them to live and die in a metal box, so that the 13th generation might set foot on alien rock. It is in the assumption that the destination matters more than the journey, that the goal justifies the cost, that humanity is a flag to be planted rather than a lived experience to be protected. I think about the children, the ones born in Generation 6, in Generation 9, in Generation 12. Children who will never feel grass between their toes, never swim in a lake, never hear birdsong outside a recording, never run freely in an open field. Children who will grow up knowing that their entire life is a transition, a bridge between ancestors they never knew and descendants they will never meet. Children who will ask why and receive an answer that amounts to, because people who died 200 years ago decided this for you. Are we willing to create those children? Are we willing to look them in the eye, metaphorically, across the centuries, and say, your suffering is acceptable because it serves the mission? I am not saying we should never go to the stars. I am saying we should go wisely. We should go in ways that do not require us to sacrifice our humanity to reach our destination. We should go when we are ready. Whoa.